Suppose we take a 9-volt battery and connect it to a 60 microfarad capacitor. And what happens is this is the positive end of the battery, so it builds up a positive charge here and a negative charge here. And we can use Q equals CV to find out that it is 9 times 60, 540 microcoulombs. Okay, so far so good. Now we take that charged capacitor and we connect it to a 20 microfarad capacitor. This is a kind of weird situation. Are these in series or in parallel? It kind of looks like they're both, right? It's just making one loop. But let's think about what's going to happen here. When we connect to these, some of the charge is going to flow over here. We're going to gain some charge over here and some negative charge over here, and we're going to lose some there, and then things will eventually settle down. How much charge will there be and where when they settle down? What's the condition? Well, we know that Q1 equals C1V1, and we know that Q2 equals C2V2. They don't have the same capacitance. They shouldn't have the same amount of charge on them. But what they do have in common is the voltage. They are connecting the same two pieces of metal, so they are in parallel, and V1 equals V2. From this, we can tell how much charge ends up on each. So we have Q1 over C1 equals Q2 over C2, rearranging. And if we put in C1 is 60 and C2 is 20, multiply both sides by 60 microfarads, and we get Q1 is equal to 3 Q2. All right, but how much charge is that? The other thing that has to be the same in this situation is the total charge. There's no place else for the charge to escape to. We connect these together. The positive has to be all together on those plates. The total, 540 microcoulombs, is equal to Q1 plus Q2. So using this, and Q1 equals 3Q2, we get 4Q2 is 540, divide by 4, and we get 135 microcoulombs is Q2. And so Q1 is 405 microcoulombs. What's the common voltage that they have at the end? Is it going to be 9 volts or is it going to be less? Well, it seems as if the charge has been allowed to spread out, which is sort of easing the pressure. So there really ought to be less energy than before. So let's figure out how much. Well, we know Q1 and C1, and we get 6.75 volts. Now, what about the energy? What was the total energy beforehand and the total energy afterwards? Well, the energy before was 1/2 CV squared. So that's 1/2 60 microfarads times 9 volts squared, 2,430 microjoules. So that's the energy in the original system. How much energy is left when it splits up? We have U final, and we total up the final energy in 1 and 2, we get 1822.5 joules, down from 2430. We seem to have lost a quarter of the energy. Here's another way we could have gotten that final energy. Treating these capacitors in parallel, we could view it as just being one big 80 microfarad capacitor, and just doing 80 with that voltage would have given us the same answer. Finally, let's consider what would happen if there was a resistor here. Does that change anything? The total charge is still the total charge. They do end up at the same voltage because once it settles down, there's no current flowing anymore. And so the resistor might as well be a wire. So the final voltages have to match, and the total charge has to match. So we could solve the same equations and we'd get exactly the same results. So what did the resistor do? The resistor is what ate the missing energy. That's where it went. Realistically, there's always going to be some amount of resistance, even in wires, and this is just making it more explicit.